Welcome to Pale Blue Pod, the astronomy podcast for people who are overwhelmed by the universe but want to be its friend.
Oh, that's nice. That's us. Hi, I am Dr. Moiya McTier. I'm an astrophysicist and a folklorist and a friend to the universe.
Yeah. And I'm Corinne Caputo. I'm a writer and a friend to the universe and a friend to Moiya, a friend to listeners.
Mm-hmm. A friend to all.
A friend to all.
As we've said before.
Yeah. I love where we are right now because I love any excuse to get a cup of coffee. And we are at a beachside coffee shop in Florida.
Yes, we can't do that in New York.
No, they don't let you sit on the
beach. Well, I mean, you can do it, but you just wouldn't
You're totally right.
to do it. It's nice that we're down here where there's still warmth.
Getting some sun, which I always forget really puts me in a good mood.
Oh,
Yeah.
I guess that makes sense. You're like most people, and you're not like me with a vehement hatred for the sun. That's
I will
good.
not sit in direct sunlight, ever. I need to be under shade, but I like when it is sunny.
Okay. Another one of Corinne's cool takes. I don't like the sun, although every once in a while I will go into plant mode and I'll just sit in a sunbeam, very much like Cosmo, my cat. And the sun is cool though. It's related to today's topic in that the sun gives off a lot of X-rays.
Yeah.
So many X-rays. And today we are going to be talking about a specific telescope that observes in the X-ray. It's the Chandra X-ray Observatory.
Woo!
Yay! Claps for the Chandra X-ray Observatory, which is a NASA-operated telescope that is up in space, actively orbiting us right now, and learning a lot about the X-ray distribution of the universe. And one of the first things that we learned about X-rays is that the sun is really bright in them.
Yeah, I'm sure.
Had you ever heard of this telescope before we started doing Pale Blue Pod?
I don't think so. I think only from you.
Yeah, it's not a famous telescope by any means, but it is one of NASA's, and I quote, great observatories. There are a handful of observatories that NASA has poured a lot of resources and energy into in the different regions of the electromagnetic spectrum. There's the Hubble Space Observatory and now JWST. Both of those are in the optical. The Spitzer Space Telescope is an infrared one, and Chandra is their, like, does flagship always mean the first, or does it mean, like, biggest and most important?
I think I think of it as, like the headquarters.
Yeah.
But I think it is typically first.
Okay. Because this was not first. We're going to get into the history of X-ray observatories in a second, but...
No, you're right. The best or most important thing owned by particular org.
Awesome. Yay. Then it wasn't the first X-ray observatory that NASA launched into space, but it was the biggest and best, and is the biggest and best to this day that NASA has put out there. So let's get into the history of X-rays and us using them to learn about the universe. We talked a little bit about the history of X-rays in general back in the light episode, which is episode 6 or 7.
Yeah, really early.
Way back. Mm-hmm. But X-rays were discovered by a German scientist, Wilhelm Röntgen, in 1895. It was a complete and total accident. He was running electrical currents through something called a Crookes tube. Okay, it's Crookes, a Crookes tube. It produced an invisible type of light that, like, he couldn't see this light, but he put something, like a piece of thick paper, behind the tube and noticed that there was still light on the other side of the piece of paper, and it was like way too far away to just be a reflection of the light that was coming off of the tube. So in this kind of roundabout way, he realized that he had found this new energy. He didn't even realize it was light at first, but he had found this new energy that could pass through objects, paper, even like human skin.
Whoa.
He called it X because he didn't know what it was, and he was like, this X energy can pass through things. But it was confirmed in 1912, so 17 years later, to be another type of light, another part of the electromagnetic spectrum. The wavelengths of X-ray light will range from 0.1 to 10 nanometers. So they are very small. This is the second most energetic type of light. Only gamma rays are more energetic than X-rays. So their wavelengths are really, really tiny, and their frequencies are really, really high.
Mm-hmm.
We can produce X-rays in the lab by sending electrical currents through tubes filled with gas, but in space they are produced by objects that are really, really hot. I'm talking millions of degrees, or things that are really energetic or really chaotic. So you see X-rays being emitted by supernovae, which are stellar explosions. They are both hot and energetic. Pulsars, accretion disks around black holes. Those are thermal X-ray sources. And then they are hard to study, or they have been hard to study in the past, because X-rays don't pass through our atmosphere. Their wavelengths are so short, they're actually shorter than the average distance between molecules in our atmosphere. So the X-rays just get bounced around, and they don't reach the surface of the Earth. So we have to put our X-ray observatories or detectors high up in the Earth's atmosphere on planes or old weather balloons is what they used to do. And now we just launch them out of orbit so that they don't have to deal with the atmosphere at all.
Oh, cool. I've definitely seen some kind of illustration of that as these little squiggles that are not coming towards us, but
yeah.
get chaotic over there.
Mm-hmm, mm-hmm. Yeah, our atmosphere and our magnetic field protect us from a lot of things out in space before they reach the surface of the Earth. So thank you, atmosphere, and let's definitely continue to protect that ozone layer. X-rays, so they bounce around in the atmosphere and they don't reach the surface of the Earth, but they're also difficult to detect because they will pass right through a mirror. No matter how fine you make the mirror, it's not going to reflect an X-ray photon because the photon is just so energetic. So you can't make an X-ray telescope like other telescopes with just a mirror on one end because it will pass right through. So you have to get creative. And what we've discovered is that X-ray photons will, if they approach a mirror at the right angle, they will graze off of it. So if you have a photon that approaches at a almost parallel angle to the mirror, it's almost 0 degrees, then it will just hit it and it'll glance off, and then you can redirect that towards a focal point. So most telescopes, like optical and infrared telescopes or radio dishes, they are shaped like a dish, or they have a lens or a mirror that is shaped like a dish, and it is meant to focus light to a particular focal point. You can't do that with X-ray telescopes. They have to be tube or barrel shaped. So you end up with something that looks like a long telescope that Galileo would have used.
Right.
And actually, the Chandra Observatory kind of looks like the telescope. It's about the same size and shape as the telescope that Galileo used in the 1600s, but it's not an optical telescope.
It does look like that.
Yeah. It looks the same, but it works in a completely different way, which is pretty cool. The first imaging X-ray telescopes were made by a team of scientists under the direction of, I'm assuming, an Italian, maybe Italian-American scientist named Riccardo Giacconi. He was at the American Science and Engineering Institute in Cambridge in Massachusetts. So we owe X-ray imaging to him. But let me tell you how we got there.
Yeah.
So the origin of X-ray observations, unfortunately, starts with the military, as so many things do in astronomy. In 1923, the U.S. Navy opened a research facility somewhere, I don't remember, and they were interested in X-rays for their potential for shortwave radio communication. And they called it radio communication, even though it was X-rays and not radio waves, because people had this association between radio and hearing, which, hurts my heart, but whatever. It's fine. So X-rays, the military was trying to use X-rays for this shortwave radio communication, and I imagine shortwave is better because it can travel farther maybe, or carry more intense signals with more information in it. I'm not totally sure, but they were interested in it. And at that research base, they also started studying the upper levels of Earth's atmosphere. where they detected some X-rays at high altitude. So they decided to launch rockets with detectors that could get high enough to study that part of the atmosphere more. And they were doing that for 40 years, studying the atmosphere, realizing that there's a bunch of X-rays there, and developing X-ray detectors and imagers so that we could study that more. In 1962, we launched the first rocket that had an X-ray detector, not an imager, on it. That rocket breached the atmosphere for just under 6 minutes. It was 350 seconds. And in those 5 minutes and 50 seconds, they detected the first ever X-ray source that wasn't our sun. It was detected in the constellation Scorpius, so they called it Scorpius X1 because it's the first X-ray source. And it turned out to be a binary system of stars where one of them is like really big and powerful and giving off a lot of X-rays. And then there was like this explosion of X-ray astronomy, which it was pretty incredible. The next year, in 1963, we took the first ever X-ray picture of the sun. That was with Giacconi's X-ray imager that was put on a rocket-borne telescope and was launched out of the NASA Goddard Space Flight Center with some collaborators. And it took the first X-ray image of the sun and revealed that there was a diffuse X-ray background coming from the entire sky. So that prompted extra research because people were like, where are all of these X-ray photons coming from? What are they doing? What are they telling us about the parts of the universe that we can't see with our eyes? Over the next 7 years, astronomers discovered 40 more X-ray sources besides our sun. It was the Crab Nebula pulsar, which is now a really well-studied region of the sky. They discovered supernova remnants. They discovered what they originally were calling X-ray stars, but it ended up being neutron stars and black holes. They discovered the galaxy M87, or like the X-ray components of this galaxy. It is a huge galaxy with a lot of other galaxies in a cluster, and it was the first source of X-rays outside of the Milky Way that we ever detected. So in the 40 years, we really ballooned X-ray astronomy from like, we don't even know how to study the universe in X-rays to we've found all these sources and it's coming from a lot of different types of things in the sky. So we learned that X-rays were prevalent and that they were going to be an effective tool for mapping and probing the universe because the things we're interested in, the hot stars, the energetic black holes, they are the things giving off all of these X-rays. And before they were like harder to study than some other things. In 1970, NASA launched, I want to say it was the first like satellite just dedicated to X-ray astronomy. It was called uhuru, which is the Swahili word for freedom. And they called it that because they were launching it from Kenya on the 7th anniversary of Kenya's independence, which is very exciting. So they launched uhuru. It was a pretty simple instrument. All it could do was essentially like count the number of X-ray photons coming from different regions of the sky, but it wasn't very sophisticated and it wasn't very precise. Still, it let them map the sky in X-rays. They did like a pretty cursory all-sky survey with it. It provided the first observational evidence for black holes because it saw the accretion disks around black holes, and accretion disks get really hot and then they emit thermal X-rays. It revealed that galaxy clusters have a lot of hot X-ray emitting gas in them instead of just being, a bunch of galaxies with empty space in the middle. It also charted the behavior of neutron stars in binary systems to tell us how they behave when they're near another star. And it was so successful that it paved the way for future X-ray devoted missions. So pretty quickly after that, NASA put the Apollo telescope mount on the orbiting craft called Skylab. This was the first orbiting X-ray processor that had more than just that one simple instrument. And then NASA launched the Einstein telescope, which was the first imaging X-ray observatory with like a full suite of instruments on it. But it wasn't just NASA getting into the X-ray astronomy game. European space agencies were also very much on top of it. The European Space Agency, which is mostly like the UK, they put out Exosat and XMM Newton. These are two pretty well-performing X-ray telescopes. The Germans put out Rosat, which stood for the Röntgen satellite, named for Wilhelm Röntgen, and other countries around the world started to put out some X-ray detectors. But none of them were as ambitious as the Chandra X-ray Observatory, which was initially, like for the very first time, outlined in a research proposal by Riccardo Giacconi and some of his colleagues in 1963. That's when they started sketching out the Chandra X-ray telescope.
Yeah.
That was just 9 months after Giacconi's X-ray detector had been used to find Scorpius X1.
I love that. It's like, let's go.
Yeah, he was raring, you know, like he had a plan.
Yeah.
So that first sketch for the proposal happens in 1963. In 1976, Giacconi and one of his colleagues named Harvey Tannenbaum, which to me sounds like someone who needs to be a character in a Christmas movie.
I was going to say, it sounds like a fake name of some fictional person who's either like beloved or like the villain.
Yeah, exactly. Or maybe a villain at first with a redemption arc to be beloved. Yeah, that's Harvey Tannenbaum. No, he was an X-ray astronomer, and together they submitted a proposal to NASA called For the Study of the 1.2 meter X-ray Telescope National Observatory. Essentially, they were proposing the world's finest full suite X-ray observatory to be launched into space in 1976, knowing full well that the technology to get the type of performance requirements they were looking for didn't exist. It was a very ambitious plan from the beginning. They had science objectives and performance requirements that weren't possible with 1976 technology, and yet NASA approved their proposal. The next year, NASA approved funding for conceptual design and preliminary analysis of a mission that was then known as the Advanced X-ray Astrophysics Facility, or AXAF. Calling it a facility may have been a kind of strategic move. The people at NASA liked calling it a facility instead of a telescope because Congress had just approved funding for the Hubble Space Telescope. And scientists are always on their marketing shit. Like, we always have to be promoting our work in a way that's going to be memorable and palatable to the people who fund it, i.e., the government or military in most cases. And so they didn't want to call it a telescope because then Congress would be like, but we just gave you money for a telescope.
Sure.
I love that back then they were like, they're not gonna know that the difference between optical and X-ray is important. They will just hear that it's another telescope.
Yeah.
So yeah, they called it a facility. And the very next year, in 1977, they started building out plans and like doing some preliminary testing at the Marshall Space Flight Center in Alabama with some science help from people at the Harvard-Smithsonian Astrophysical Observatory, which right now it's in Cambridge. It's off of Harvard's campus. I think it's one of the biggest collections of research astronomers in the world. There are like 500 research astronomers there right now.
That's a lot.
I don't know what it was like back in 1976, but they had a background or they were known for doing some high energy astrophysics work. They had like a solar physics research facility there. In the 1980s, every decade, the astronomy community gets together and they put together the decadal survey, which determines what the community wants to prioritize for the next 10 years. And in the 1980s, the decadal survey called AXAF the number one priority for large space-based missions. That was in the 1980s. I'll tell you that AXAF, which then came to be known as Chandra, didn't launch until 1999. So
that took a while.
It took 23 years from proposal to launch. And I read this article by Martin Weisskopf, who was involved in planning this over not the whole 22 years, but for like a decade of that. He worked at the Harvard Smithsonian Astrophysical Observatory, and he was brought on to this kind of be its champion because it had been floundering for over a decade by that point. I think it was 1992 maybe that he was brought on to the team. But I read this blog post or whatever that he wrote giving his personal account of the planning and the preparation of Chandra. And he said his impression was that even though the decadal survey put AXAF as one of its top priorities for the next decade, he said that it seemed like it just had to wait its turn after Hubble. And that's why it took 22 years.
Yeah.
Yeah.
That's annoying.
It's really annoying. And in those 22 years, the project changed quite a bit. It still met and exceeded the performance requirements that Giacconi initially put forward, but that's because of advances in technology that happened over those 22 years. Mm-hmm. They ended up cutting 4 of the mirrors that were planned. It was originally going to be 12, 6 pairs, and then they took 2 of the pairs away. They took a couple of the positioning thrusters away and simplified that whole mechanism. They removed 2 instruments that were planned to be put on the telescope, and they even shifted away from a model where the telescope would be serviced regularly like Hubble. And so they put it out at a further orbit and made it so that it wouldn't be regularly serviced and fixed by people, which gave it a shorter lifespan. But I think it's already surpassed its projected lifespan. In 1998, they renamed it the Chandra X-ray Observatory after NASA had one of its contests where they were asking the public to name things.
They love those contests.
They love those contests.
And so do I.
Yeah, me too. Because it's nice that it's not just a bunch of old white dudes in the NASA administrator office deciding what everything is called.
And it's the research here is for all of us. Obviously, a group of people can use it well, the trained academics, but I love the kind of approach of, this space is for all.
Yeah, because it is. It belongs to all of us, and we are all a part of it. But they named it Chandra after a really prolific physicist named Subramanian Chandrasekhar, who did a lot of cool stuff in theoretical physics. I know his work around black holes and white dwarfs, where the Chandrasekhar limit for white dwarfs is the limit where they will go supernova if they're in a binary pair. So Chandrasekhar, great scientist. I don't know what he was like as a person, so I'm not going to say he was a great dude because we've all been burned by that before. But he was a great scientist, and they named this telescope after him, and then the telescope was going to be operated out of the Smithsonian Astrophysical Observatory. So that is where the Chandra X-ray Center is to this day. Right now, the Chandra X-ray Center is operated or led by a man named Dr. Pat Slane, but right before him, the director of the CXC was Dr. Belinda Wilkes, who advised one of my projects in undergrad. We just did an episode about my research, and one of the projects I listed for my undergrad was studying a quasar, a very active black hole, and that was the project that she advised.
Cool.
She was nice. She's very, no-nonsense lady.
Yeah, sure.
Yeah, I respected her a lot.
Hey, it's Corinne. It's a great time to thank our patrons who support the show every single month. So thank you, as always, to our Sun-like stars, Sharon Llewellyn, Lissa, and Ian O'Leary. And you can support us, hear your name on the show, and make it to our patron star chart, all by supporting us on Patreon for just about $1 per episode. And if you sign up for an annual membership, you get a 13% discount. Find the star chart, Patreon info, and more at our website, palebluepod.com, or by going right to patreon.com/palebluepod. And if you can't support us financially, that's totally fine. We love you very much. You can support us by reviewing the show on whatever app you use and by sharing the show with your friends. If you're loving Pale Blue Pod, and especially if you're loving Dr. Moiya McTier, you must give her other podcast, Exolore, a listen. If you didn't know, Moiya is a folklorist. I think we talk about it a lot on the show. But if you've ever wondered what life would be like on different planets or how writers create your favorite fictional worlds, Moiya has the facts for you. On ExoLore, Moiya explores fictional worlds by building them with a panel of expert guests, interviewing professional world builders, and reviewing the merits of worlds that have already been built. You will learn, you will laugh, and you will gain an appreciation for how special our planet really is. It is the perfect companion pod to Pale Blue Pod. You can subscribe today by searching ExoLore on your podcast app or by going to exolorepod.com. This episode is also sponsored by Ravensburger Puzzles. Indulge in the timeless pleasure of assembling Ravensburger extraordinary jigsaw puzzles. Ravensburger's premium quality puzzles are crafted with meticulous attention to detail, bringing you an unparalleled puzzle-solving experience. There's a rich heritage dating back to 1883. Ravensburger puzzles have become an integral part of families' lives across generations. Share the joy of puzzling with family and friends, knowing that your cherished puzzles will stand the test of time. Enjoy a mindful moment and immerse yourself in a world of captivating colors, stunning imagery, and intricate designs that will delight people of all ages. Regardless of your preferences or skill level, you'll find a jigsaw puzzle that suits you perfectly. Thanks to a wide range of imagery, themes, and piece counts, you can start small and work your way up to over 40,000 pieces. Shop Ravensburger on Amazon today. Okay, back to the show.
Okay, so 1998 is when it gets renamed to Chandra, and then it launches in 1999. Between 1976 and 1999, the U.S. alone had launched several other X-ray telescopes and observatories, including Einstein, which was like a pretty good telescope. But when it launched, it was it performed like 10 times better than the other telescopes that had been launched because it was planned with such specific requirements. Like they wanted sub-arc second resolution, which I now realize is a term that probably doesn't mean much to many people, but they wanted the telescope to be able to see really tiny things far away.
Yeah.
It launched with the Space Shuttle Columbia on July 23rd, 1999. Eileen Collins was named the mission commander for that space shuttle flight, and she was the first female commander in the history of the U.S. space program.
All right.
Yeah, good for her. But any like reactions to that history?
I think I'm just delighted that it actually got launched after all that time. I think my personality leans pessimistic, so I would have just, in that 20 years, would have just been like, never gonna happen.
I think a lot of people thought it wouldn't happen. Yeah, but it did. And when it launched, and now, some specs, some details about the telescope itself. It's taken us a little bit to get here. Chandra, how heavy do you think it is?
Oh my gosh, I feel like I have no concept of this. I don't even know.
How big do you think it is?
I think it's probably as big as like a car, as like a Subaru Forester or something.
All right. Way bigger. It is, with its solar panels fully spread out, it is not a solid, like, cube, but it is 45 feet by 64 feet.
Wow, that's huge.
It's big, and it weighs 10,560 pounds.
Wow, that's heavy and expensive to launch, I'm sure.
Yes. Yeah, it probably cost, like, millions of dollars. I actually didn't look up the pricing of this. I should have, but I didn't. It has an elliptical orbit around the Earth. At its widest, the orbit takes it 80,000 miles away from us, so it's about a third of the way to the moon. Mm-hmm. And at its closest, it's just 16,000 miles away from us. It takes about 64 hours and change for Chandra to orbit the Earth once.
Long day.
It's a long day. You're right. It has three main parts to the whole kit and caboodle. There's the spacecraft itself, which like took the telescope and the instruments up into space and provides like a safe environment for the telescope and instruments, and also like makes sure that it's positioned correctly. So there are two sets of thrusters on the spacecraft that let it point where it wants to be pointing. Because this isn't a survey mission. It's not like doing a pre-planned scan of the sky. is doing requested observations. So it needs to be able to point to specific places in the sky. So there's the spacecraft, and then there's the telescope. And the telescope is the thing that collects the light. The instruments are the things that analyze the light. So you have the telescope, which is an X-ray telescope, so it's not shaped like a dish or a mirror. It's shaped like these long tubes. There are 4 of those mirrors, and they all focus the X-ray photons towards a focal point, and the instruments are behind that focal point. So the telescope gathers the X-ray photons and then sends it to the instruments. There are 4 instruments on board the Chandra spacecraft. 2 of them sit right at that focal point, so they can analyze the photons like immediately. The first one is called the high resolution camera, which is a very self-explanatory name.
I was going to say, what a simple name.
It takes high resolution images. But it is one of the instruments that sits right at that focal point, where the glancing tubes have directed the X-ray photons. The camera has 0.5 arcsecond resolution, which means its eyesight is good enough to read a newspaper half a mile away.
That's really good.
It's really good, and it's so much better than the resolution we had on previous X-ray imagers. There are some side-by-side comparisons of like the Crab Pulsar Nebula, for example, with like pictures that the Einstein telescope took versus pictures that Chandra took, and Einstein looks just like a fuzzy blur. And the Chandra image has all this beautiful like detail where you can see individual little filaments in the cloud. It's gorgeous. So yeah, its resolution so much better than previous telescopes. This high resolution camera works by having an array of tubes filled with gas, very similar to Röntgen's original experiment that found X-rays in the first place. So you have these tubes filled with gas, and they have been specially calibrated to X-ray photons so that when a photon hits one of the tubes, it produces an electron that has a specific energy, and then that energy is read by the camera and produces an image that like reflects where the X-ray photons were. So it can tell you where the X-ray photon came from in the sky, and that gives you the image. The high-resolution camera, which they shortened to HRC, and the first time I read that, I was like, Hillary Clinton?
Yeah, it is. That's so funny. It is like, that is the much more popular version of that now.
It's so weird being an astronomer because, you know, we love our acronyms and our initialisms. And so there are so many little, like, acronyms that people use in everyday life that, like, I have associations with astronomy things for them. Like, people in non-astronomy spaces will often talk about, like, the IMF. And I don't know what they think IMF means, but to me, IMF is the initial mass function. So, like, there is a lot of things like that. So the HRC, which is not Hillary Clinton, but is the high-resolution camera, is especially useful for imaging hot matter in supernova remnants. It's really good at looking at distant galaxies and galaxy clusters because it's good at identifying faint sources, and that is all because of its high resolution. The other instrument that sits right at that focal point is the Advanced CCD Imaging Spectrometer. It can make X-ray images and measure the strength of each individual X-ray photon. So because you get the strength of the photon, it's kind of like spectrometry. The strength of the photon tells you the energy of the photon, which corresponds to a specific molecule. Like, that's how spectroscopy works. So with this camera, you can actually isolate specific energies of X-ray photons that correspond to specific molecules. So you can make a map of the oxygen in a supernova remnant versus the carbon versus the nitrogen, all because of this X-ray spectrometry that we have going on. But then there are 2 other spectrometers on Chandra. There's the high and low energy transmission grating spectrometer. A grating spectrometer is just like a special type that's really good for X-rays. And it just, like a prism does with regular sunlight, it splits it up into the wavelengths so you can measure the strength at each wavelength. And those are the 4 instruments, and we regularly get this data downlinked to Earth from the satellite, and astronomers can use that data. And eventually, after a proprietary period, usually around a year, that data is publicly available. Because it is funded by NASA, meaning it is funded by taxpayers, and they deserve to have access to the data.
Yeah.
Like I said before, the telescope is operated out of the SAO. The Chandra X-ray Center is at Harvard, and they put out regular calls for proposals. Their last call ended in March of 2023, so there will probably be another call in the next 6 months or so. I think they do it on a yearly schedule.
I was going to ask, because you had said that they position it and it looks at stuff, and I was wondering if it was a similar process to the other telescopes
similar.
we've talked about.
Very similar. Yeah, any astronomer can put together a proposal that says what they want to observe, where it's going to be and when, and why it's going to add to our understanding of the universe. And then there's a committee, a time allocation committee that looks through the proposals and decides what is a good use of the telescope's time. And then they select the projects, and then they operate the telescope to carry out those observations at the right time. The Chandra website is not as forthcoming with information about director discretionary time, or whether or not other countries get a set amount of time on it, which makes me think other countries don't. Hubble has that 30% that has to go to European astronomers. I don't think Chandra has anything like that. And over the last 24 years that Chandra has been in operation, it has made some really cool discoveries. We have learned so much about the existence of supernovae and what they leave behind. We've learned so much about black holes. We now use Chandra and X-rays to study dark energy and get a sense for how that behaves on long-term and long distance scales. So it's learned a lot, but here are a couple discoveries that it has made. In 2017, I think, Chandra imaged Cassiopeia A, which is a really well-studied and well-known remnant of a supernova that went off about 350 years ago, we think. And it's about 11,000 light years away from us. I think still in the galaxy, but I'm not sure. The image showed the location of different molecules in the cloud because of those spectrometers that are on board. So we were able to see Cassiopeia A in oxygen and Cassiopeia A in other elements too, which let us trace the things that happened right before the supernova went off. So our understanding before this was that as a star, a massive star, is burning through its fuel in its core, it's making heavier and heavier elements in its core. So there's hydrogen on the outside, but then iron in the core. So in the supernova remnant, we would expect all of the iron in the cloud to be near the center. But with this image of Cassiopeia A, they saw iron further out in the cloud than they expected, which implied that there's some sort of mixing happening either right before the supernova goes off or right after it. And so it told us something that then revealed just a bunch of other questions we had to ask next.
Yeah.
Which is how you know science is working.
Yeah.
Chandra and the European Space Agency's XMM Newton telescope, which actually launched the exact same year, both of them made it possible for us to measure black hole spin. We have an episode on black holes from a while ago, but in that episode we talk about how there are 3 numbers that you can use to describe a black hole, and those are the only 3 numbers you really need. You need to know the black hole's mass, which we have been able to measure just by looking at the motion of stars around black holes. You need to know the black hole's charge, electrical charge, and most of them we can think of as electrically neutral, but they're not actually completely neutral, and there are other ways to measure the charge. But before Chandra and XMM Newton, we knew that black holes were spinning. Einstein, when he talked about black holes, he imagined that they would be spinning. But we didn't have a way to measure that spin. And with Chandra and XMM Newton, they could measure the rotation of the black hole by seeing the effect that rotation had on iron emission lines. So like if the black hole is spinning, then those emission lines get spread out. So that was cool. It helped us understand black holes better. And remember the very first X-ray detection back in 1962 or 63, what they learned, in addition to taking a picture of the sun, was that there is just like a continuum of X-ray noise out in the universe. We were able to confirm that all of that X-ray noise is coming from many, many thousands of supermassive black holes in the universe, in other galaxies that we couldn't see with optical or infrared telescopes because they were too weak or there was too much gas and stuff in the way. But with X-rays, with a really powerful X-ray telescope, they could see those things. And so now we know what the X-ray background noise is.
Cool. That's so fun.
Yeah. And there are so many headlines with news discoveries from Chandra, and I linked to some of them in the research notes for this week that patrons have access to for every single episode. But those were the big three that caught my eye right away.
Yeah, I'm surprised that I didn't really know Chandra.
I'm not.
Yeah.
X-ray astronomy doesn't get a lot of attention in the press because it's not giving us much more information that the public actually cares about than optical or infrared telescopes. So people are much more interested in the pretty images and in like big flashy topics like exoplanets. So because Chandra doesn't really do that, it doesn't get as much focus.
Well, now Chandra gets her due.
Let's give Chandra her flowers. But Corinne, I'm curious. If you were asked to design your own X-ray telescope, what would it do? Because they talked about Chandra. They planned Chandra starting in 1963, where we didn't have the technology necessary to do it yet.
Yeah.
So, we don't have to have the technology yet, but what would you want an X-ray telescope to do?
Well, I think I have a silly answer, which is I'm thinking about how... it can see a newspaper from half a mile away. And what if it was here on Earth and it helped me see stuff I wanted to see? It's like getting a superpower of I have X-ray vision of a sort. I think I would use it to read the script of a show that I love from far away.
Okay, but Corinne, you could do that with an optical telescope if it's just to read newspapers.
You're right. I guess my only agenda is to spoil television shows. So I'm like, what will this do for me?
You're not even trying to spy on your neighbors or anything?
I think I will. I think I'll turn it to that. But I don't really want to ruin people's privacy. I just if I got spoilers for a TV show, I wouldn't leak it. I would just get to no. Maybe I would look at when Thanksgiving season is behind us, but Trader Joe's puts out my favorite turkey chips every year. They're stuffing flavored. And then I could see when they get the delivery without calling like a crazy person. I could be even crazier.
All of these things.
Yeah, they're insane.
No, they are nowhere near as insane as you could have gone with this question. I think that you are being extremely restrained.
What would you do?
Well, I would start like a spying thing. I would do a little espionage. I don't know. I would launch a rocket with a X-ray telescope that points back to Earth, and it would have imagers, but different imagers that are tuned to different strengths of X-ray photons that can penetrate different types of substances. And I'm going somewhere with this because I don't think we have this technology yet, but similar to the spectroscopy where you are looking at different strengths of X-ray photons to get at different molecules, I think that one day maybe we'll have technology that can isolate a specific wavelength of X-ray photon that can only look through cotton but can't look through skin. And like that is the type of X-ray vision that would actually let you spy on naked people.
Yes.
Because if the X-ray photon can also go through their skin, then you're just seeing their bones. So what I want...
I don't want to be looking at skeletons.
Yeah, exactly.
So you'd have to tailor
sometimes I do. Sometimes I do. Do you not sometimes just wonder what a person's skeleton looks like, Corinne?
Oh, I do, but I think that I would get legitimately scared if I saw like a skeleton family sitting down to dinner.
Right. Fair. Yeah, so the Moiya X-ray telescope would be able to have essentially like a little switch that you flip and say, I want to look through clothes. I want to look through skin. I want to look through metal boxes. And those are the ones where you can like look inside delivery trucks to see what's in there.
Ooh, yeah. I don't know. My instinct is like, well, I want my life to stay exactly the same, but with like small, tiny perks of like, without wreaking any kind of havoc.
And I'm like, I want to be able to gather all of the information, both private and commercial.
Yes, you want to be the keeper of all the info.
I mean, does that not match who I am right now?
I think it fits.
Like,
I do think it fits.
I want to know everything. And my X-ray telescope would let me know everything.
I love it. It'll only take 20 years. Plus
That's
many
it.
more.
Yeah. We have to wait for the next big, great observatory to launch.
Just
and
send your
it'll
proposal,
be my turn.
and maybe they can point it back to Earth and then change all the things Chandra can do.
That's not a bad idea.
I think you got time.
In the last episode, we came up with a TV show. Now we're coming up with the
perfect proposal.
Yeah. We're crushing it, Corinne.
We're in idea machines.
We are. Do you have ideas for other things you would like to know about Chandra or X-ray observatories before we sign off?
You know, I think after this, I'm going to look up how big that size is compared to the car I mentioned, just to fully grasp how large Chandra is.
Yeah, I think it would be like 4 or 5 cars bumper to bumper.
Ooh, yeah, that is so big.
Yeah, and then like 4 cars stacked.
Yeah, cool.
Pretty big.
Well, wherever you are today, whether you are in a coffee shop, by the beach, or looking through people's clothes, I hope you remember that you are space.
Yeah, you are. You little voyeuristic freaks.
Yeah, don't do that.
Pale Blue Pod was created by Moiya McTier and Corinne Caputo with help from the Multitude Productions team. Our theme music is by Evan Johnston and our cover art is by Shay McMullen. Our audio editing is handled by the incomparable Misha Stanton.
Stay in touch with us and the universe by following @PaleBluePod on Twitter and Instagram, or check out our website, palebluepod.com. We're a member of Multitude, an independent podcast collective and production studio. If you like Pale Blue Pod, you will love the other shows that live on our website at multitude.productions.
If you want to support Pale Blue Pod financially, join our community over at patreon.com/palebluepod. For just about $1 per episode, you get a shout out on one of our shows and access to director's commentary for each episode. The very best way, though, to help Pale Blue Pod grow is to share it with your friends. So send this episode, this link, to one person who you think will like it, and we will appreciate you for forever.
Thanks for listening to Pale Blue Pod. You'll hear us again next week.
Bye.